Alright, hey guys, what's going on? So today we are going to be talking about SU3 interactions in the Lagrangian. Again, if you like this kind of content, make sure to hit that like and subscribe button. Let's get to the content. Okay, so again, if you like this kind of content, make sure to hit like and subscribe. You can also hit up my Patreon page where you'll find exclusive content as well. So when we're talking about SU3 interactions, this is where we're going to get into quarks. Quarks are super interesting. This is really going to help us solidify and understand what exactly particles are when we're talking about Lagrangians and when we're talking about all the stuff that we've been talking about. The first thing that we want to do is recall the SU2 interactions and the SU2 transformations. Okay, the SU2 interactions, again, those gave us W and Z bosons. Okay, and those were the weak interactions. We talked about that. In this case, in the case of the transformations, remember that when we transformed an object in the Lagrangian, this is how we were transforming it, whether it be a local or a global transformation. This is what it looked like, and this was a 2D matrix, okay? Because when you exponentiate a Pauli matrix, the thing you're going to get is some sort of 2D matrix that does a rotation, okay? Recall that these transformations must be Lorentz if we want to get any interesting physics out of this. The Lorentz transformations must be Minkowski metric preserving. So is there a set of 3x3 matrices that will sort of obey this property? Okay. Remember that the Lorentz condition was something like this, where we had, say, a matrix. In the case of our Pauli matrices, they looked something like this. And this was I, J, K, K. Right, so this was the condition that had to be met in order for it to be a legitimate representation of the Lorentz transformation. So a lot of physicists, including Murray Gell-Mann, were interested in this kind of question. They came up with a set of matrices, essentially, that obeyed this condition up here. And these are what the matrices look like, okay? This is one such representation. There are many others that we can think about, but these are the ones that are going to give us the interesting quark physics, okay? And we'll see why. So just like this was our generator for the SU2 transformations, what we're going to do is we're going to say that TA equals 1/2 of lambda A, right? And these TAs are going to be the generators, okay? So it's just going to be 1/2. These are all lambdas, right? It's going to be 1/2 of these guys, okay? And those are going to be the generators. All right, let's do an example. So we can demonstrate that these generators are obey that Lorentz transformation condition, which is going to be this. So, which is very similar to this. This thing is anti-symmetric, so FABC is also going to turn out to be anti-symmetric. We're just going to do an example here. So let's take A equals 1 and 2. So A equals TA, TB, so these guys are going to be 1 and 2. This is 1, and this is 2, this is 2, and this is 1. This is that commutation relationship. And then what we do is we take we do the matrix multiplication, which is going to look like this, and we see that one is the negative of the other, so we can add essentially this because we're taking a negative out, and now we have both of the same thing, and we get 1/2 I equals 1/2 this, which is I equals F123. So that's F123 is going to be 1/2, and TC again is right here. Okay. So actually what I want to do is say 3. Oop, don't want to do that in red. 3. All right, and so we have shown just through an example, we can do this with many other examples. I think this is just the easiest way to sort of conceptualize this in our heads is through an example that this relationship indeed holds. The structure constants, these F guys right here, all look like this, right? So, and they're all anti-symmetric. We can calculate them in this way. We're not going to go through that derivation. That if that's something you want to see, then that's something I'll maybe put as exclusive content on my Patreon page. But the point here, again, is that these guys here are the structure constants. Again, those are these right here, or more generally, these right here. These are all anti-symmetric, making them a part of the Lorentz algebra. Right, so this is how these two relationships look very similar to one another, right? And so we feel comfortable in saying that these 3x3 matrices obey this Lorentz algebra, okay? And therefore, they are legitimate matrices we can use to transform the Lagrangian, which is now, well, not quite yet, but which is what we will do in a bit here. So there are 3 subgroups within SU3, okay? These guys here, and these guys here, where X and Y are linear combinations of lambda 3 and lambda 8. This got erased. I'll write that again. All right, so what we can say here is that we saw that TA and T2 gave lambda 3. Okay, so those fall into this circle right here. They were a closed group. We can see here that 4 and 5, we can do this multiplication. I'm not going to do it right now because I think it's just matrix multiplication. You should be able to do this kind of stuff. But what I kind of want to do is just organize this and show you where the interesting physics is going to come from here. We can say, okay, this guy here, or this guy here is this circle right here, and this guy right here is this circle right here. So these are all subgroups within the larger group of the Lorentz transformation. They're all glued together. All these are glued together by lambda 3. Okay? Which is interesting in its own right. But what we can do now is what I was talking about earlier. We can put this we could put these guys in an SU3 Lagrangian. There's a few things to note here. So since there's 8 matrices, we need 8 spin 1 objects to retain the SU3 local invariance. So this leads us to think, okay, there's going to be 8 of these spin 1 or gauge fields or particles, right? So in the case of the SU2, we had the W and Z bosons. In the case of U1, we had the photons, electromagnetic interactions. So in this case, we're going to be saying these are gluons. And the name gluon is going to be reminiscent of the particles that make quarks glued together, which is why they're called gluons. And we'll see exactly why this is the case. So this is what our Lagrangian looks like. Really, this isn't that much different than what we've been seeing, right? It's just we have Q's now, because we want to distinguish between Q and psi, where psi was the invariant object. Psi was, if you recall, the invariant object for the SU2 case, or not the invariant object, but the dynamic object in the Lagrangian for the SU2 case. Q we're going to reserve for the SU3 case. Okay. So, and again, this is the Dirac equation. This really isn't that much different than what we've been seeing before. So you might ask, well, okay, if it's not that much different, then where's the interesting physics gonna be here? Well, the interesting physics is going to come from the fact that we have 8 generators, and we'll see. I'm getting to this right now. So what we have is, so if we want this to again to be locally invariant, this local invariance, we need to replace this d mu with this d mu right here, right? And you might think, okay, well, what's the difference between this lowercase d mu and this uppercase d mu? One is a covariant derivative, right? This is what we've been doing up to this point. We've been saying, well, if we want local invariance, we need a spin 1 field to interact with these objects, and the spin 1 field is encapsulated in the derivative, which is what we'll see in a few seconds here. I'll just get to the point here. This is that relationship, right? It's right here, right? We've seen this before in the case of bosons, right? In the case of bosons, this was the relationship, okay, where this guy here could have been truncated. I put the whole thing, but this guy here could have been truncated to something that just looks like that, right? So we have, and this guy here is truncated to something that looks like this, right? So we have these objects but these are spin 1 objects that retain local invariance, and these things have to interact with our quarks. I'm skipping to the point here. These things are going to be quarks, which is why we're calling them Q. But there has to be that, in order to have that local invariance, the theme we've been seeing up to this point is we need to have a spin 1 field interacting so that we can retain that local invariance, okay? So that we can bring again, if you go all the way back to when we've talked about this, the whole process of retaining local invariance was the process of having a derivative in the Lagrangian that looked like this, and having e to the, say, I alpha x, right? And our thing and our field, and we wanted to bring this over to the other side of the derivative. But in order to do that, we needed to have that spin 1 field in order to make this work, and in order for things to remain invariant. So this local invariance is in order to have this local invariance, the theme, we're still on point with the theme, again, which is to bring spin 1 fields into interactions. Okay, I'm beating a dead horse here, but I don't really care that much. This here, again, is the self-interaction term for the gluons. We've seen that before also. In the case for actually, I'll be more consistent here. In the case for U1, we had this, and in the case for SU2, we had that. Okay. All right, so okay, and so the things are pretty much the same. We had a 1/4, we had a 1/4. And I'll write these out. This was for the SU, or not SU. This was for the U1 case, and this was for the SU2 case. Okay. Anyways, that is sort of neither here nor there. Right now we're talking about SU3, which is what these guys are. So, okay, here's where the physics is going to come in. So, okay, what we did in the last couple of videos is we said, okay, these things, we have leptons. The leptons were, we had particles, electrons, muons, tauons, and these all consisted of leptons. And the leptons consisted also of their corresponding neutrinos. So we had the electron neutrino, mu neutrino, and the tau neutrino. And these were three guys associated with three Pauli matrices, essentially, but those were encapsulated in these guys here. We had three of them. So, okay, we might think, okay, well, we have 8 gluons. We have 8 gluons. So maybe we'll have 8 states here, okay? These were doublets. These are going to be triplets. However, I'm crossing these two guys out because 3 and 8, if we go back to 3 and 8 here, these things could be made up of linear combinations of these, right? So 3 and 8 are unique in that they can be made up of linear combinations of any of the, if you choose the right ones here, of these guys, right? So what we do then is we say that we're going to get rid of the two. We're going to get rid of 2 of them, okay? So this is weird, right? Because we have, so what we have here are 6 of them, okay? 2 of them of which are going to give us the eigenvalues for what we're going to be looking at next. So if we return to the Venn diagram, we're going to say that this upper circle is going to give us up and down quarks. We're going to say that this circle here, this is where the physics gets implied. This circle right here is going to give us the top and bottom quarks, and this circle right here is going to give us the charm and strange quarks. Okay, so this is where we're being suggestive on the physics. Okay, we are saying that the up and down quarks and the so we have the different types of quarks. Okay, these are the fundamental particles. And then these 2 guys in here, we're going to say, are going to give us the eigenvalues, or the measurable things that we can detect upon that transformation of the Lagrangian. So these things right here are, when we transform the Lagrangian, there's going to be eigenvalues to those transformations. Those eigenvalues are going to be given to us by these 2 matrices. In a different basis, they can be given to us by a different set of matrices. But we're just going to choose these 2, and we're going to say that the eigenvalues for gamma 3 are 1/2, 0, and -1/2. When we look at the matrix, the eigenvalues for gamma 8 are going to be 1/2, or 1/2√3, 1/2√3, and those come from these 2 entries, and then negative 1/√3 because of this 2 right here. And so anything that starts with a 1/2 is going to be considered red color charge. Anything with a -1/2 is going to consider to be called having a blue color charge. And with that 0, with anything that has that 0, is going to be something that's considered a green color charge. And so, okay, so what we can do, we can organize this a little bit differently. We can say that the -1/2 and +1/2, okay, these 2 guys have those 2 other eigenvalues that come from lambda 8. And then this guy here has that eigenvalue of 1/√3. The eigenvectors for each one are going to be right here. Okay, and so what we can, so what we're saying is that the subgroups give us the particle types, right? So These guys are going to give us the particle types, up, down, charm, strange, top, bottom. And so those subgroups are going to give us the particle types, and the eigenvalues of the transformation will give us a conserved quantity. Okay? And last but not least, we now want to fill in the triplets and what they actually look like. So we're going to have a triplet that has up, up, down. We're going to have a triplet that has up, down, down. We're going to have a triplet that has charm, charm, strange, charm, strange, strange, top, top, bottom, and bottom, top, top. And you might think, are these the only ones? Theoretically, no, right? You can have up, 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 down, down, down. But the things that we've measured are protons and neutrons that that have up, up, down, and up, down, down. Okay, you need one of these two combinations to make up the quarks that live inside of the nucleus of the atom. Why? Well, this is experimental. I'm more of a theoretical person when it comes to this physics kind of stuff. But if this is something that you're interested in, understanding why exactly, then perhaps we will go over this in a separate playlist. We are really coming to an end here of the of this kind of stuff, and what I want to do in the next video is briefly consider grand unified theories, and then we're going to cover everything that we've gone over in the last, say, 20 videos or so. And what I'm thinking about doing is making a summary that you guys can all keep for yourselves and have it look nice, have it look like a nice PDF file or something like that. Have it be something that I'll put on my Patreon page or go and I'll go over it maybe. But if this again is something you like, we've talked about quarks now, we've talked about leptons, we've talked about so much stuff that I think it's about time to now move on to the next topic, which is you guys have spoken, and that's going to be differential geometry. Differential geometry is super interesting. We're going to pick this up. We're going to start picking this up within the next few videos as well. So with that being said, I hope you guys enjoy this kind of content. Again, make sure to hit that like and subscribe button. There's going to be no exclusive content on this video. I want to share quarks with you. I think they're super interesting. But with that being said, have a great rest of your day, and I will see you guys in the next video.